got lucky to be here and see old friends and new friends and see so much of great mathematics, and I have a chance to discuss it with people who actually really understand it, and I'm grateful in every possible way, mathematically and as a person. So it's certainly worth to take the flight from Western United States to Heathrow and do everything I'm supposed to do to enjoy this meeting. So I would like to talk about positive scalar curvature metrics on manifolds with fiber singularities, and some words here probably are a little bit from foreign land in this meeting. So what I would like to do, I would like to briefly take you to the environment which is relevant to this particular work. And for a moment, I would like to think about just a manifold, and for a moment again closed manifold. And then we think about metric. And I'm not sure how many people here thought about metric on the manifold. I know several, for sure. But there is for metric G, there is a very important invariant which is called scalar curvature metric, scalar curvature of given metric. And so I would, I think about this particular invariant for quite a while, and I know, and I have to confess, I have to say that I know that there is more and more to learn about this particular invariant. So what's going on? So at the simple geometrical level, so it didn't come from thin air. And nobody just, there's not that somebody just thought, okay, let's study this invariant just in case. So if you are thinking in terms of, the relativity theory, or so Einstein theory, that you know that the scalar curvature is it's a kind of density in the actual functional. What you do, you take integral and you divide by volume of your manifold in the power n over -2. And what I wrote here is known as Einstein-Hilbert functional. And then what you can do, you can actually take a look at the critical points of this functional. And critical points of this functional, critical points of this functional are just exactly Einstein metrics. And of course, originally it was done in Lorentz setting, but it actually makes perfect sense in Riemann setting. Then just we freeze the time, and this is what we get. So critical points are Einstein metrics. And particularly important type of critical points, critical metric Einstein metrics, when scalar curvature or Ricci curvature will be 0, so it's so-called vacuum. But then it is important that this density function becomes positive. Then there is something else going on in your manifold. So this is was essentially origin of the for scalar curvature. And then the second phase, when manifold N happens to be spin, this is the case that I'm most interested in, then metric G gives Dirac operator, which lives on in the corresponding place. And if you think about, say, manifold, that manifold M has dimension D, then all Dirac operators live in, if at least connected component will be KOD. And then, so this Dirac operator represents just nothing but, we have a spin Morrison class maps to there, and this is what we call index of Dirac operator.
Is N the same as D?
Yeah.
Yeah, that's what I was
Sorry, so I have to put either N or D. So let's actually let me stick with N, because then I will get confused completely in what will follow. So, what else is happening? We know that if index of Dirac operator is non-zero, then there is no metric of positive scalar curvature on that. And it follows from Lechnerovich formula, which says that Dirac operator squared is some spin or Laplacian plus 1/4 of the scalar curvature of the metric. Then if it's so, if this is positive operator, then then it's forced to be in Dirac operator is forced to be invertible, and then it means that index has to be 0. So this is where what was known, like maybe in the beginning of 60s, and then after developing of index theory, there are several results due to Hitchin, but I won't give you the whole history, the whole story. So let me jump to the following theorem. Rolf Lawson and I should add Stefan Stolz here. So, and it's actually looks like this. Let M be simply connected, and dimension M greater than 5. Then one case, if M is spin, first not spin. Second case, M is spin. Then there is a positive scalar curvature metric. And M always, and then here there is a positive scalar curvature metric, if and only if. And now I'll say it in the way we all understand in topology. Alpha invariant of M is equal to 0 in KOM, which is the same as to say the index of Dirac operator is equal to 0. And so this is for geometers at that time, and I witnessed that when some geometers I had to when this paper came out in 78, 79, some people asked me to explain what's the geometry behind this. And it's actually difficult to explain. However, there is a very important point here, that if you are a geometer and you have your manifold M, and it comes with some way, it comes with some metric, 32. Then you try to decide, does it have metric of positive scalar curvature? And it's not easy. So locally, you can always do that. And then, even in this case, if it's not spin, maybe you need an abstraction, maybe not. So it's actually, it does look like a magic that there exists such a metric. And without topology, it's not possible. What's the trick here? the point is that in both cases, in one and the other case, if abstraction is zero, what is possible? It's possible to make surgery on M to get new manifold called M prime of the same dimension, so that this manifold is certainly has positive scalar curvature, and it's in non-spin case it will be just homogeneous space, which naturally has. So what is going on here? This case is reduced to omega SO star. This case is reduced to omega spin star. So in for oriented boardism, we know generators, and what happens is we can actually take your manifold and do surgeries, but surgeries have to be of right kind, for dimension at least 3. And then you show that this manifold splits into pieces which have positive scalar curvature. And there is no way to determine this just by looking at your manifold and try to solve some PDE. It's not possible. So it's actually in this sense, yeah. And then in the case of spin, so some part of this was done by Gromov and Lawson back in '79, and then Stefan showed the following, that this index map has a kernel which you can describe as, let me actually put this here, as a, so there's a very particular group, Lie group SP3. It happens to be a symmetry group on HP2 with standard metric. And then, so this, then there's a transfer map. If you map it here, then you can take HP2, and structure group will be a symmetry group. And then what you do, you take manifold here, and it has positive scalar curvature. So this part is easy, but this next part was not trivial at all. That to show that one has to show that the kernel of this is covered by the image of this transfer map. This was basically his major achievement in this particular theorem. Okay, so from this, what else I would like to mention, that assuming that we know that both, so in the same spin case, we know that there is a metric of positive scalar curvature. Sometimes we know this for obvious reason. When we have, say, a sphere or projective space, we know this for sure. What is the space of positive scalar curvature metrics on given manifold M, on sphere, or and then this is something that was done quite recently, and the point here is this, that so you look at the space of metrics of positive scalar curvature. Let me actually think about sphere. And then you choose metric G0, which is a, say, standard metric on the sphere. And then for any other metric, which may be far away, what you can do, you can take interval of metrics. It's a convex space. And then you look at GT here, and then in the other space of appropriate space of Dirac operators, you have a loop, a curve which starts and ends at the subspace of invertible Dirac operators, right? And then in this space is actually really great in the sense that subspace is contractible. When you get a map from this space to the, well, let me actually put this in the right notations, n plus 1, of KO. So meaning that there is a particular dimension, and what this is what we call index difference map.
What do you mean by omega?
Sorry?
What does omega n plus 1 KO mean?
Well, it's homotopy group. It's KO n plus 1.
Okay.
So I don't want to kind of
Just
go
a loop,
through
okay.
the kind of all this. I don't want to kind of confuse maybe some notations with others. And this is so-called index difference map. Difference map, and what we show that with Oscar and Johannes Siebert, that this map is non-trivial in all homotopy groups, and so if dimension n is at least 6, and then there is some other method to show that it's true for n is greater or equal than 5, and that's so it's a surprising kind of result. But I would like to point out something interesting here, that if you look at non-spin manifold, we know that space is non-empty, but we know essentially nothing about the topology of the space. So it's an open question. This is one of the motivation for this work, and frankly, there's much more than I will tell you, but it's there's some other cases. But I would like to kind of start some definitions and maybe explain what is going on. So I would like to define what does it mean, manifold with fiber singularities. It's not very sophisticated object. You have a closed manifold P, and secretly I would like for us to P to be equal to a circle, or actually future. So we're trying to understand some other situations like SU or SU2. But anyway, and also we understood the other very nice case when we zero at K. But so it's closed manifold, closed manifold. And then we have now I would like to forget that my manifold is just closed. Now it has a boundary, and boundary, so we have manifold M, which comes with a boundary, and boundary is a fiber over some other manifold, closed manifold, which we have notation beta M, with a smooth fiber bundle over beta M with the fiber P. Well, it's so there are many examples. When P is a circle bundle, one can imagine many of them. Now, then it's an ordinary manifold with boundary with some extra structure. Now I would like to think about maybe some other graph M. So let me put a little bit different picture, but it's relevant. So I would like to look at cone over this manifold P, and I would like to denote corresponding fiber, corresponding total space is as n of beta m. So what we do, we have our P and we have a cone, and then, by the way, if we have a cone over S1, we have a disk, so it will be just normal bundle of this beta m. And then, so what I would like to do, I would like to take M sigma is the M union with, we have to take orientation into account, and together with this, we glue together these two pieces. One is a normal manifold, and there is a singularity over the submanifold. So in some other literature, it's called pseudo-manifold with two strata. One can think about this as a, there is a one, so there is a beta m which lives its happy life inside of M sigma, and you delete this beta M and you have open manifold, and then you have particular structure near this submanifold beta M. Okay, so it's pretty obvious what's going on for any topologist. So, nevertheless,
What is n of beta n?
so it's so you insert colon of over P instead of P in this fiber bundle.
So it's the fiber-wise cone.
Yes, fiber-wise colon over P over
Thing you
beta.
started with, I see.
So, and this is you can think about P. This is colon of P. This is where we glue them together. So now then one can think about metric of Riemannian metric G on this object. And what it would be? Well, it's there is some obviously it has to kind of be compatible with the structure. Now, from now on, I would like to actually to be more specific, and I would like to think about only this case, because only here I have something to say. And now, so we have circle also. It's a group, and I would like to think about action on this circle action on this tubular neighborhood, which is quite obvious. And now I would like to think about G as a metric on M sigma. So it has to be C0 metric on the whole manifold. And also it's regular if you restrict on M sigma without beta M, it's a regular Riemannian metric. Okay, then, and if you restrict G on the neighborhood, I would like for this to be the following. It's actually cone metric over P. In our case, is circle cone metric on C of P, and plus we lift some metric from the box line from the base. So it's a specific type of metric. So I would like to kind of give a name to this. I would like to call this metric cone metric near singular stratum. Cone metric near singular stratum. Near singular stratum. Okay. Now,
So in the case when P is S1, the cone is actually a smooth manifold again?
well, if yes,
So,
but it's
so M sigma is actually.
so if P is S1, it's actually is a smooth metric. In
But-
many other cases,
Sure, but in this case, this is not a metric in the usual sense.
it is a metric in the usual sense, but with this condition that it's actually cone metric. So circle, so it actually invariant under circle action near the singular stratum. Okay. That makes sense?
And it's actually smooth when you move towards the stratum. It's actually a smooth section of the two zero tensors.
Yeah.
Oh.
Yeah, so in this case, it's actually just, you can think about as a smooth manifold with. So this is why kind of, it's actually at this particular point, when we say fiber singularity, so it's not really singularity. But it actually gives when we, for instance, you can think about spin C manifold, which is not spin. And you think about manifold, which is dual to the first, to the first Chern class, and then it plays the role of beta M. So it will be manifold with a structure that there is a submanifold of codimension 2, and there is a together with a normal bundle. about circle action. Let me give you examples. This example, no, before example, there is a one geometrical fact which is very important here. Okay, so let's take some. It takes some. Right. So there's a theorem by Gerard Berger. So which it's a very old theorem, by the way. It's so I have manifold X, closed manifold with free S1 action. And then let me X over S1, the orbit space, which is a manifold, is symmetric if and only if X has S1 invariant, X1 invariant metric AC. Okay, so this is no, it's not very difficult geometrical fact, but it's not well known actually. So we have to kind of produce some kind of proof of this. It's not so difficult. So let me look at examples. In dimension 4, everybody knows K3 surface. And K3 surface has certain particular features. Well, it's H2 with Z coefficients. I think it has 22 generators, and also a head genus is not 0, so it doesn't have does not have a positive scalar curvature.
Boris, what's the rank of H2?
Ah,
What is the rank of H2?
22.
22. Okay.
22.
I think you said 82. And, yeah.
Not 82, 22. So what you can do, you can actually take this surface. No, it's with there are many constructions of this surface. It's one of the kind of famous Calabian manifold. And then sorry, I have to master my skills. Then what you can do, you can actually choose a primary class in H2 and send it to CP infinity and define take the S1 bundle, and you have manifold X. And manifold X is of dimension 5, and it's manifold X of dimension 5, and then it's actually is a boundary of some manifold M, spin manifold M of dimension 6, by simple reason that omega spin 5 is 0. So there's some very really trivial facts, but they're quite useful. So then what this one, we take M, and now we form M sigma, and then we can take this bundle of this over this K3, and this manifold is not spin, but it's actually spin C. One can actually check that this is spin C by just looking carefully at this diagram and take into account that this is a primary class. Then what we have from Gromov-Lawson, we know that this has positive scalar curvature metric, And this is now regular smooth manifold. But now what we can actually say that this metric of positive scalar curvature never restricts to the disk bundle, which would have the appropriate structure, which would be S1 invariant. Why? Because otherwise we would get a problem that we would have S1 invariant metric on X5, which would project to positive scalar curvature here, which does not exist. So this is first example. Now let me take another example. We have so we have exotic sphere of dimension 10, the one which projects to KO 10, non-trivially, and then it has no positive scalar curvature metric. But then what we can do, we can actually take this sphere and delete a disk. This will be my manifold M without disk. And this manifold M has a boundary S9, which is fibers over projector space, and it has positive scalar curvature, of course, but it does not extend to the whole M. So what I'm trying to say that there is a different type of abstractions here which we have to analyze. Different type of abstractions here which we have to analyze. One more example of the same sort. Again, let me think about the same. There's some mistake here. So we take this sigma 10. It's a great manifold, and a lighted manifold when you connect it some with CP5. This is so-called fake homotopy projector space. And this one also doesn't have, this projects to non-zero in KO. It also doesn't have positive scalar curvature. But what's going on is there's a sphere of, there is actually a homotopy sphere of dimension 11, and the fiber, actually, I would like to say something in an easy way. So there is a map to CP infinity, which is generator of CP5. Then you get the total space, and you can check that this is actually a homotopy sphere of dimension 11, and which is also a boundary of some manifold M of dimension 12. And then again, what you do, you take M together with the disk bundle, N of sigma 10 together with CP5. And then what happens is this new manifold M sigma is spin C again, as in the first example. And what else is going on? It's simply connected. Spin C does have metric of positive scalar curvature, many of them, but this metric is never conical near the singular stratum. This is something that, at least before we started this work, I haven't seen. So then what you do, when you kind of know some topology, you kind of try to understand how to put this together and see if there is some reasonable way to detect that there exists metric of positive scalar curvature in such objects. Okay, so okay, sorry, I'm a little bit lost. Okay, so now, of course, one has to think about relevant Bordizing group. This is, as everybody here, it's easy to define. And in this case, it actually turns out to be not so difficult to compute, but it's still kind of easy to define. So what we can think about, so let me work now with only the following situation when we have original manifold M has to be spin. Then this new manifold spin M sigma, not necessarily spin, but sometimes it is spin. So what we have here spin N, and we have a group which we call N spin S1 fiber singularities. So one can think about this group as just manifold M, and also the structure of fiber bundle with the fiber S1, and then everything here is spin. Then Bodism between these objects is obvious, and you construct this Bodism group, and you have that there is a natural homomorphism here, which takes manifold to make closed manifold, and this one is empty. Then we have a when you think about this structure, then there are essentially a couple of cases to consider. Because what's going on, this one is spin, so W2 is 0. Of course, W2 is 0 here. But then you look at you look at this beta M. And beta M, well, it's actually maybe convenient to think about also a map to CP infinity, which classifies this bundle. Then and we also can think about one more line bundle, complex line bundle that you got it from there. And then there is of course, this is C1 of L. And then what you can do, you can look at W2 of this beta M, right? W2 of this beta M, it lifts here to 0. In cohomology, it goes to 0. But then we know that actually kernel of this is given by C1 of L mod 2. So then it means the following, that either, so there is one case when the bundle is trivial. So we have, so L is trivial. Then both manifold beta M is also spin. But then in other case, if it's not trivial, then so then W2 is just equal to C1 of L mod 2. So which gives essentially two cases. You can go to spin group together with the map to CP infinity, or you actually get honestly spin C manifold. This is what we get. This is Bockstein actually gives you a map to homomorphism to n-2 of CP infinity spin, and also n-2 just spin C. We actually, for a while, we were arguing that, is it possible or not, but, there are examples where, there's a one manifold, and there's a boundary, which pieces will give you spin, this piece which will give you non-spin. And then there is an obvious transfer map. I don't want to, clearly it goes in a different degree, but so you have map to CP infinity, you have take a circle bundle, you map it here, and here you use canonical spin structure, spin C structure to get circle bundle, you get it here.
It goes into degree n-1.
In degree n-1, absolutely. When you look at this in coefficients, it's actually, then you can show that this is 0. This particular transfer map is 0. So these groups basically splits into these two pieces. Okay, so then what is going on? Then, of course, we'd like to think about some group KOM as one FB. This is KOM. This is actually a combination of groups KOM and plus. I don't want to kind of spell out everything. And then we have a homomorphism to this group, which we call alpha S1 FB. And we essentially compute this group. And the theorem we have is the following, that if we have a manifold M here, plus omega M, spin S1. Now we are talking about the positive scalar curvature on this object. So we would like to assume that M, then del M and beta M are all simply connected. And dimension of the whole thing is at least 7. And then we show that this manifold is symmetric in the sense I described, conical near beta M, if and only if its image B of the M, this M is 0 in this group KO, I call it KO, and S1. Alright, so again, the way one can prove such things is, there are two important components that if that map here index, so we have to understand all index theory here and see if index is non-zero, that it's not possible for two or three actually different reasons. Depends on the situation, on many for them. And then there is the second part, which is harder part, to show that kernel of this would be generated by objects which we can actually give a positive scalar curvature. This is where we use, besides HP2 bundles, we use we use CP2 bundles, and essentially we show that there is a transfer map here, so that every element here is generated by either HP2 or CP2 bundles, where we have kind of, and by the way, the major computation with CP2 bundles was done, sorry, I forgot his name is Furgen. So he's I think he's a student of Bernd Hanke. So he did computation which we have to reproduce again essentially, but it's this is not needed. So now, so I have a little bit more time to say something else. First of all, that we consider this as a part of story where we would like to understand, besides this case, cases of other Lie groups, first of all of SU2. This is where, the kind of, so for people who thought about positive scalar curvature, clearly this is actually has flat metric, this has quite non-trivial metric with positive scalar curvature, and then, so the whole kind of flavor here is quite different. And it leads to, frankly, it leads to some non-trivial analytical problems which we did not resolve completely now. So what does it mean to have properly defined Dirac operator on object with these fiber singularities? But there are some, we work in this project with, besides, I work with this project besides Jonathan with Paolo Piazza, we hope to get something else. But this is kind of more the timer, but there is something else here which I would like to say, and I think it's quite important. So let me go back to this kind of where was it? Let me think about spin C manifolds for a moment. For spin C manifolds, if it's simply connected and not spin, as we've seen in many examples, there is some kind of a non-trivial situation. But on one hand, there is a metric of positive scalar curvature. On the other hand, it can be never the standard near given hypersurface. So then what we did, we tried to kind of understand what does it mean in maybe a little bit different language. So, and essentially the construction, not construction, but if we look at M closed now, spin C, now, and not spin, let me actually emphasize it. And in general, what is really spin C? It's not just manifold, and it actually comes together with a line bundle, which gives you spin C structure. Then there is a like in Stockbook, we can say what's the mean borders in between these two manifolds like this and so on. Now, but here we have always, if you fix a metric and fix connection A on L, then we have a corresponding Dirac operator, which has the, there is a similar formula, and we have also, besides scalar curvature, a curvature form. Let me put it as F. I will ignore what it is. I don't want to explain, but I will even put this together as a one item. And I would like to call it, so what is it? It's actually not a scalar function at all. It's actually zero order operator, which acts on spin. And let me actually call it as a twisted scalar curvature by this connection. Now then, and clearly, there is a clear indication that if this operator is positive, then operator has to have index 0, because of this formula. This is positive operator. And what we do, we show two things. First of all, that positivity of this operator, twisted scalar curvature, actually survives under surgeries of codimension at least 3, number one. Number two, we show that if we think about spin C, spin Cn, homomorphism to Kun, complex K theory. Let me call it just alpha C. And then we show that if we have co-dimension, or dimension n at least, now actually will be against 7, then this operator will have metric and connection with this operator positive, if and only if this index of corresponding map, corresponding manifold is equal to 0. And this, so it's still, we have a puzzle here, because inside of metrics of positive scalar curvature on such a manifold, there is some subspace with this, when there is, so that this operator is positive. And we know that this, well, so I think I conjecture that this actually subspace has at least as many homotopy groups. So this actually, there is a index corresponding index difference map to K theory, which would indicate that this subspace of metrics actually has lots of topology. And on the other hand, we know nothing about the whole space of positive scalar curvature metrics. So, well, let me end up with a conjecture that, which I hope that some, much younger people will prove that, that if you take a not positive scalar curvature, but the twisted, the positive scalar curvature, but twisted on M, and there is an index difference map to Ku, actually not, it's only homotopy, has to be n plus 1 of Ku, that this map is not really homotopy groups. And it's it's a good, very good problem for graduate student. At this point, I don't have relevant graduate student to work with, but it's this is something that I hope will be done. Okay, I don't want to kind of maybe I should stop. Thank you.
Questions?
Are these borders and groups with, no, the other ones, the one with spin and S1 5, are they homotopy groups of spectra?
This one,
Yeah.
it splits as a, at least at the low homotopy groups, it splits as a sum of this and this.
Yeah, no, but my question was, are these borders and groups sort of, are they actually homotopy of spectra?
Yes, yes,
Yeah,
you
yeah.
can actually define homology theory, and so at the lower spectra, so it's I'm not sure this is actually, I can claim this. When we have splitting at the level of homotopy groups, it doesn't always imply. So it's we actually try to make this mistake. we made fun of each other.
I had a question early on. You said if you just set out trying to solve this PDE, you couldn't really tell whether there are any metrics of positive scalar curvature in this fashion. But once you've actually shown this, do you learn things about the space of solutions to the PDE?
Well, it's actually I kind of my strange kind of appealing to a strange way to appeal to PDE. Well, it's what is really happening that even if you know that there exists a positive scalar curvature metric according to this theorem, then you have your manifold delivered to you. You open the box, you see your metric, and then this metric may be billions of miles away from metric of positive scalar curvature. You don't know. You try to change it, but good luck. It's actually maybe really, really far away. This is actually something that in differential geometry you know, you'll be surprised how many people do not realize that actually metric you have is nothing to do with maybe a metric which it has positive scalar curvature. So there is all, you know, you cannot perturb it easily. There's another.
Are you saying the space is not connected?
Oh yeah, space of metrics of positive scalar curvature is not connected, and you know, at least if maybe if it's any use, I can give you an example. So as said, this is a nice manifold, and then you look at so-called Bott manifold. This Bott manifold is a, you know, has very particular structure. And then what you can do, you can delete two disks in the top and in the bottom, you know, your choice. And then what you do, you take a standard metric here, and as we say, push it through the bodies by, you know, looking at the, taking so-called Gromov-Lawson construction in there, and you end up here with the metric G0 prime. And you know what? This metric cannot be positive scalar curvature. Why? Because if it is, I mean, it cannot be standard, because otherwise you can cap it back, and you get metric of positive scalar curvature on the manifold B, and this is, there is abstraction. And this type of and this means that this metric is, it cannot be in the same path component in particular. If it is, you can do the same and still cap it and get positive scalar curvature. But moreover, we know that there are some lots of homotopy groups in the space of metrics. This one, many, and most of these homotopy groups we know are non-trivial, but we do not have explicit construction of families. We know that the corresponding map is non-zero. Geometers don't like it, but we have to work harder to explain that this is actually sometimes is not possible.
So maybe more discussion over biscuits? Oh, so I beg your pardon.
Yeah, it's okay. Just a
No.
quickie. There must be some geometric things you can say about this space of these metrics. Are there any local properties or?
Well, it's you know, so it's actually, you know, it's not from the viewpoint of standard analysis. It's not such a big mystery. So you look at the space of metrics, all metrics, with, you know, I think you think about this as a kind of sections, smooth sections in corresponding bundles of, you know, positively determined tensors, two tensors, and then scalar curvature, positive scalar curvature gives you an open subset there.
That's not much information.
It's not much information. But if you actually are after more something less trivial, I mean, there is a space of metrics with the following property that it has Dirac operator which is invertible. And this is actually, you know, really interesting and in some way mysterious space, because clearly positive scalar curvature metrics are inside of this space. But this space I just mentioned has wonderful property. You actually can perturb metric near a given point, and then, so it's actually open dense. And that's, so it's we still are struggling to kind of understand all these relationships there, but well, the conditions are very natural.
Thank you.
Can I say thank you for your patience and, you know.
Thank you.